Great, thank you. Thanks, Federico, for the introduction, and to all the organizers for the invitation. It's really an honor to be here, and hearing Federico brought me back to the days when I was a student at the community college. Actually, some work that I'll talk about today was not inspired by those days, but kind of motivated by my interest in physics. As a student there, I started there as a member of the basketball team. And I was a student athlete, and I was more interested in sports, and I thought, what could I do? And I said, well, maybe I'll do something with computers. And I ended up taking calculus and introductory physics classes, and they were the hardest, the toughest experiences I had at that point. I struggled. I had to get a tutor. I really just did not know what was going on. My first experience with higher mathematics. But it turned out that I really enjoyed the struggle. And eventually I decided to switch my major, to the surprise of family members and various professors. And it's one of the best decisions I ever made. And like I said, Federico's words, I thought were interesting bringing up the community college, because now I'm back to a question about physics and related mathematics. And so the basic question that inspired some of the work, not the exact one I'm interested in, is how are galaxies formed? Okay, informally, a galaxy is a huge collection of stars together with dust and all sorts of media that are bound together by their gravitational interaction. All right, one of the first people to really pick this study up was Yakov Zeldovich. He's an interesting guy. As you see here, he's obviously pretty decorated to make it on a stamp. But he was self-made, self-studied, according to Wikipedia, and autodidactic. So he taught himself, but he eventually made a lot of contributions to the Russian atomic bomb efforts, and then later came back to academia and picked this problem up. And he really wanted to know how are these galaxies formed. And one paper that influenced a lot of work. Okay, I don't want you to read everything, but it's one that I spent a lot of time up, which is why I wanted to post it. And here's where he lays out some of the basic mathematics involved. And okay, it's a vast problem, many, many features. But one thing he wanted to focus on was the expansion of matter without pressure. Just understand that mathematically. And then also the presence of shock waves. And so what I'll talk today is a little bit about some of these mathematical aspects and some differential equations that are involved. Now, this is firmly grounded in physics. And so just to make sure we're clear, I wanted to start out with this elementary idea of inelastic, a so-called perfectly inelastic collision. And here is drawn, we could imagine having two masses that move at a fixed rate, at fixed velocity, so they move at constant speeds, v1 and v2, and they undergo a perfectly inelastic collision if, when they collide, the masses add, and the new velocity, this v you see here in the upper right-hand side, is chosen so that this equation holds. This is none other than the conservation of momentum. It's very elementary. I look at it another way as well, and just think of this new velocity, the one that this bigger mass assumes, is just the mass average of the previous ones. If I divide by m1 plus m2, I see that the v is just the mass average. And there's nothing really specific here about two particles. Any number of particles could collide, and if they undergo an inelastic collision, the new velocity is simply the mass average. Okay, well, I want to consider the physical system, or a physical system where I have n masses that interact only via collisions. Okay, so they could be stationary or just moving freely, And when they collide, they undergo perfectly elastic collisions. They join, they form bigger masses. The new velocity is an average. And there could be many of them. So here's just an example. M1 and M2 we saw before. M3 could collide and make a new particle. We could have 3 particles that collide at once and make a bigger mass. I should say I'm really considering these as point masses. I'm just drawing bigger circles here just to indicate, bigger and smaller circles just to indicate the masses could be different. They need not all be uniform. Okay, and it'll be convenient for us to label these trajectories, okay, and track what these particles are doing. So I'm going to let gamma I be the path that tracks mass mi. So I wrote gamma 3 here and dotted. So in particular, M3 collides later, but gamma 3 stays with M3 no matter what it does. Okay, so it's just notational. Now, a basic property of these paths, which just follows from the way we set the system up, is that whenever they touch, so if there's some time where, say, gamma I and gamma j agree, then they agree for forever after. Just like if 2 particles come together, when they hit and collide, they'll just stay together forever after. We call that the sticky particle property, okay, illustrated here in this picture. And just to emphasize that the slopes agree. So at this, let's see. Oh, good. So at this point right here, the slopes agree. And they are just the mass average of whatever the slopes would be coming in. Right? It's just this rule of perfectly inelastic collisions. And this, again, is just a statement about conservation of momentum. But it turns out a more general fact is true. Does this thing work with the computer? No. OK. OK, and the more general fact is what I call the averaging property. It's a more general statement about conservation of momentum. Here, s is less than t. The g could be any function. And the way to think of this is that these particles, they're moving in straight lines unless they collide. And so when particles move in straight lines, their velocities are constant. But when they collide, you'd expect that something less than that would be true. In particular, if I remove the masses and the m's and the g's, then that would just say gamma it equals gamma is. Well, that's not exactly true because there are collisions. But really, this statement encodes what's happening when you have collisions. And it really is just kind of a general statement about conservation momentum. All right, and whoops. It'll be also useful for us to kind of change our point of view. This is a typical thing done in fluid mechanics. On one hand, you may want to study your fluid or your whatever's moving, your material, by tracking how particles move, but you also may just want to sit back and assume a frame of reference where you just observe what happens. And if I do that, then there are 2 logical variables to study. One is the mass density. Okay, so this is my notation for rho. And I should say, I will only consider systems with finite mass, so I just assume that the mass is 1 just to make life easier. And I'll define this variable rho t here. Okay, this is fancy mathematical notation, but it really is a simple thing. What rho t does, it's a measure in the sense that you give it a set and it just gives you a number back between 0 and 1, and it just computes whatever mass is in that set. So if you give me a set A, so that's schematically drawn on the right, rho of A just counts up whatever the masses are in this set A and spits that number out. So it's a pretty simple logic. There's a way to write it a little bit better, or a little bit more convenient mathematically, but if you're unfamiliar with that notation, don't worry about that. And the next variable is the velocity, v. Okay, this is a little bit different than what you do in fluid mechanics, because you tend to think about fluids moving all around and the velocity field being defined at every point. Here I'm thinking about looking at this physical system with m masses moving around and just specifying the velocity on the trajectories. And that's what I've I've kind of zoomed in at one location right here, and if you give me a point x, whatever the slope is at that point, I just call it v. It's not too complicated an object, okay? And so I've defined it here, and it makes sense. It's a little bit different probably than how you're used to thinking, but it's just a function pretty much on the graph. Okay, it turns out, I won't do all the details for you, or really any of the details, but it turns out rho and v together solve an equation or system of equation that express, one, the conservation of mass, and second, the conservation of momentum. This is a partial differential equation. Or actually, it's a system of partial differential equations. And it involves here the rho and the v. And now, well, usually when you study differential equations, you're thinking of taking derivatives of functions and so forth. Well, I just told you that the rho is kind of a measure, and the v was a function that really lived on a small set. But it turns out that the rho and v, there's really a well-defined notion you can give to them as solutions of this equation, okay? And so this holds in the whole space. And another thing that you're typically used to doing in differential equation is assigning initial conditions. In physics, you like to assign some initial values and try to predict what's happening later. That's why we study these models. And essentially what we've done to right now is say, all right, well, we have a solution as long as the initial, as long as the initial conditions is of this form. That is, you scatter out some masses in space, different point masses, assign numbers to each one of them, and just tell me in which direction they're initially going. So with these initial conditions, rho 0, so this picture is essentially equivalent to this rho 0. It just, there are finitely many masses. All the masses sum up to 1. And V0 is where they're all initially pointing. And we can say what happens. But now as mathematicians, a natural question to ask is there a way to solve this system of equations given any initial condition? Maybe not one that's just 4 or 5 or 100 or 1,000 masses scattered about, but maybe I give you a continuous distribution. Mass can be distributed in a bunch of ways. You could imagine it being, say, uniform on a given set, Gaussian, whatever the case may be. Can you solve these equations? All right, so again, so you want to solve these equations for given initial conditions. And it turns out it's a hard problem, and I don't know how to solve it. No one has really given a satisfying answer. There's some special cases where you can say something positive. There's a little bit of controversy about what's really true. Where there's little controversy, it turns out, is in one spatial dimension. There's good theory to be understood. And the reason I think that one dimension, so one dimension in the sense of particles move, but they're just constrained to all move in one dimension. So they all live on the real line, if you will. And there's something a little bit different. See, and when particles are in one dimension, if they're scattered on a line, they either can only be moving to each other, in which they will collide, or unless maybe some other particle will collide with them, or they'll be moving apart. In higher dimensions, you could be coming closer and closer, but miss each other and then get further and farther away, and it's just different. And it turns out that there's another inequality that's involved that I call the quantitative sticky particle property. I say it's quantitative because you see, if this is ever 0, then that's 0, in the sense that if you ever touch somewhere, then you're together forever after, but this kind of quantifies that. Another thing that's important when you're studying partial differential equations, especially ones where you don't really get explicit solutions so easily, is what other inequalities are around that kind of give information about solutions. And it turns out that this one will. And the corresponding inequality in the rho and the v variables is as follows. So, okay, I say yes, meaning yes, that there is a solution for given initial conditions that satisfies this system of equations. So this is the sticky particle system just in one spatial dimension. And this is the corresponding inequality right here. okay? And it may look a little curious to you, but it's essentially equivalent to this quantitative stickiness. All right, so I just gave you a relatively simple problem and turned it into a PDE, and I said, okay, well, we can't solve it except in 1D, and that really didn't begin to study the full physical problem, because I said as far as what Zeldovich was doing, he was really thinking of galaxies, and there's gravitational attraction involved, and to really try to address that, one needs to consider gravity amongst the particles. So here's a little schematic of 3 particles interacting gravitationally. These arrows here just mean that there's interaction between them. According to Newton, in the simplest case, the gravitational force between 2 particles varies like the inverse squared distance, and so there's kind of a natural potential energy between the particles. And we can we can write down an equation just like we did without much effort. Okay, so now particles won't move in a straight line. They'll have some interaction between them. And this is the general system of equations, ordinary differential equations, the so-called n-body problem. And it's not even easy to solve the ordinary differential equation, but let's just for a moment ignore that. We can define rho and v to be very similar to what we just did, again, except the particles don't move in straight lines. Rho just tells you the amount of mass. It's in a given set. You feed it a set, it tells you that number. And this v here just studies the velocity field along these trajectories. And just as we did, I won't give you all the details here, we can write down this system of equation called the Euler-Poisson system. And it's very similar to what we did before, except there's this interaction term. And this star here is short for convolution, and it takes the following form. Some people call it Euler-Poisson because for that particular potential we had, there's another equation that comes into play. And as I said, this is, if I couldn't solve the problem with phi, then it's hard to solve it without it. But I did tell you that there's this quantitative feature in one spatial dimension that was interesting. And so as mathematicians, we try to learn more by studying various models. And so one question that people have been really interested in is, okay, well, if I put a phi here and I restrict particles to move in one dimension, what can I say? Is there a solution or not? And in particular, is there a solution that models a situation where particles stick together and stay together? It turns out, so phi here is just any general function for the time being. And by a not too difficult analysis, I did not do it here, but I'll just tell you that if phi is concave, so phi double prime is concave up, phi double prime is bigger than 0. This is a model for attraction. So particles want to move together. And so that's illustrated right here. If phi is concave, then this is a model for repulsion. And this is also, like I said, a toy model in the theory of formation of stars and gravity. And so in this case, we'd expect a similar theory to the one I discussed before, that if particles want to attract, you'd figure they'd stick together and stay together and life would be good. But in this case, you could actually have a situation where particles break apart in so-called splitting. Now, it turns out that if you limit this, this second derivative, if the particles are repulsive or not too repulsive, in particular, if the second derivative is, say, bounded below uniformly by some number, so in particular, it could be a repulsive setting, but not too bad. It turns out that there's a completely analogous theory where we can build solutions of this equation which satisfies an entropy estimate of this form. So C, that same C there is C here. We're thinking of C being a positive number, and this is hyperbolic tangent. There's nothing to remind you what hyperbolic tangent is, but it's an increasing function. It's a nice increasing function in time. And just to illustrate, when we have that assumption that the second derivative of the interaction is not too small, so we're not too repulsive, we get a very similar situation to before. Before in the sense of the sticky particle where there's no interaction. Okay, and so here I draw these curves. They're not straight lines, again, because it's just they're interaction between the particles. And so if I take that solution V from before and I just solve these ODEs and look and see what happens between any two solutions, then we get the following inequality. Before I had 1 over t here, now I've got hyperbolic sine, which is an increasing function. Think of it being exponential. It's basically, in this case, e to the square root of c times t over 2. And so it's still, so it's not as good as we had before in the sense that it's a worse quantitative estimate, but nevertheless it quantifies what happens. And I think it will be, I think it's an interesting result that we can have some repulsion, yet particles do stick together. Okay, I want to switch gears a little bit now. So I know probably PDEs and things like this, or I know some people like Ricardo and Rodrigo and various other people do study differential equations, but not everybody does. So now's the time to check back in. I'm going to change topics a little bit, and I'm going to talk about optimization and how these equations, or equations like the ones we've been talking about, come into optimization problems. And one area is optimal mass transport. Okay, and I've got my second scientist, this time is Gaspard Monge, French mathematician, who also made it on a stamp. And from this picture, you can see he was a pretty serious guy. Okay, and so he's known for a lot of different things. One thing is just asking the following question. Okay, let's just read it out loud. How do you best move given piles of sand to fill up given holes of the same total volume? Okay, that's a pretty open-ended question if you think about it. There's so many things to consider. I mean, is there gravity? How are you moving the sand? And so forth. Well, one way to mathematize this is the following. There are probably other ways, but one way is the following. Now we're going to think of taking two measures. I always think of finite measures, and so I just take the total measure to be 1. So think of mu and nu to be two masses of equal size, let's just say 1. And I'll schematically draw these masses as follows. I try to use PowerPoint to change the effects a little bit, just so they're not necessarily uniform, right? Some of the sand, so think of on the left to be the sand. Some of the sand, maybe it's not totally uniform, and there's some clumps that are heavier to bring over, and on the other side, maybe there's some real estate, some parts of the hole that are a little bit harder to get to, and so we account for that. And we think of mapping the sand to the hole by a map T. So you give me X, piece of sand, and T of X is the location it ends up. Okay, Monge said, well, there should be some sort of cost for moving this X to this T of X. And so I think of that cost as X minus T of X squared. He really did X minus T of X distance, but I'm thinking of the square, which is fine. And then I might have moved a little bit of mass, so there's a d mu there. And if I add up all those possible transferences, I get a total cost. And so I want to minimize that among all t's, but there's a constraint. I want t to be measure preserving in some way. Okay, and so I write this T pound mu, we say T push forward mu, and this is the definition. So T pushes mu onto nu if, when I take any set over here, B, and I look at the pre-image, then mu of that is equal to nu. Okay, now it may seem more natural to you. When I was a student, this confused me. I was really worried about this. But it's better to work with the pre-image than the forward image. But if you want to think of T as an invertible map, then you could really just think of, say, any set over here, whatever measure is given to that, T of, under mu, then T of that set is the same measure under nu, which is fine. Another way to think of it in terms of probability is that, what's a good way to say it, is that nu is the distribution of T under mu. And so this is also, in fact, true for every function f. So there are a lot of ways to think about the push forward. It's kind of it's kind of like a rearrangement, if you will. Okay, so we have a minimization and a constraint. Okay, and it turns out to be kind of a tricky problem. I mean, how to really get started on it, how to attack it. Fortunately, since Monge posed this program, there has been a lot of progress on it. And 30 years ago, there was a theorem by Jan Brenier that said that, okay, if that first measure is what we call absolutely continuous, if it really has a density, so it doesn't look like mass is all separated, point mass is separated around like we first studied, but it's really a nice density, then there is an optimal map, T, and it turns out T is the gradient of a function. So that's nice. Whenever you can take a mapping problem and just extract a scalar function, that's nice. And it turns out this function size is convex, which I've schematically shown here. So it's convex, and of course, psi observes the constraint. So all these things are true, and I mean, Brenier figured out a whole lot more. But this was just part of the ideas that came out of his work. And it turns out this is really useful for us in understanding this problem. And it gives us a way to kind of interpolate, to kind of break down this mapping problem from mapping the sand to the hole and look at what happens kind of intermediate. Okay, and one thing we can do is use a certain interpolation that comes pretty naturally. Okay, and so I call this rho t. So it's the same definition before. I won't write it again, but it's of the it's the push forward of this quantity of the first measure. And I consider it an interpolation because if I put t equals 0 here, well, 0 kills this. And then the identity pushes mu, it's easy to check, is just itself. And so at 0, I just regain the shape mu. And if I go to t equals 1, well, then rho of 1 is just equal to that. And then I end up with this measure over here. But if I pick t in between, I'm just at some intermediate position. Okay? And I draw this x, the straight line here, because another thing this says is that mass is transported along straight lines. That actually is really useful. So all these positions over here, all these x's, get moved over to mu along straight lines. And just to figure out where this rho is, I just stop here at t. I just go from x to gradient psi of x at t. It's very easy. Now, one thing, I didn't really say much about the convexity. Why is it convexity? How does it come in? Well, so I won't illustrate that for you, but I will tell you that since psi is convex, it implies that as a mapping of x, this mapping here is 1-to-1. And in particular, these lines will not cross. And so mass is moved from the sand to the hole in a really organized way. In fact, psi is chosen so that this happens in the most organized or the most optimal way. And at this point, I hope you start thinking about, well, we started when I started this talk, I started talking about mass moving and colliding. One thing I didn't talk about was a situation where mass just moves in straight lines. I mean, if there's no collisions, then that's kind of the easiest situation that we would have considered. It's more interesting, of course, when there are collisions. Okay, and one more function, and this function, okay, ignore this box for a second, and just think about if I'm here on this intermediate mass, rho, t, at each point, I'm on this line, and the slope of this line, I just take a t derivative here, and what's left over is this. Each slope is given. It's just given by this, this vector right here. And so I could define a velocity field v, which essentially just points this arrow. And I can just do this on this entire mass, and it gives me a nice field. And so this formula here is really, if I wanted to write it down explicitly, but geometrically it's easy to think about. And then it turns out, from what we did before, that this rho and this v together are a solution to this equation. Okay, it's the easy case I didn't cover. If mass just moves in straight lines, there are no collisions. There are no collisions, and I get a solution pretty easily. Okay, and so I call this the collisionless solution. It's a big formula to write down, but whenever you have a situation that mass just spreads out, one can write this down. But there's actually even more. There's even more to look at here. And the way to see it, so I'm going to use this notation now. PRD. I had to invent a little bit notation. You'll see why. It just means probability measures on the whole space RD. Typically, you're thinking of R2 or R3. If I wanted to be more precise, I'd say Borel probability measures. But just think of mass distributions. Okay, you give a set, you get a number between 0 and 1. It sums on disjoint sets. Very just heuristic. The heuristics are good enough. Now, there's another quantity I can define closely related to the optimal quantity I studied before when we were studying Monge's problem. This was actually first considered by Kenarovich in various economical problems, was to find a minimum measure here. So here I'm minimizing now a function over RD cross RD, that's x minus y squared, and then I've got now a measure on the cross space, pi. Okay, so the way to think about this informally, let me go back a little bit, is if I go back to my original problem here, one could imagine studying the problem where mass splits. Instead of just taking one piece of mass to one other position, I can just take mass and distribute it how I will. And if I do that and set that up in terms of an optimization problem, it's exactly this one I have here inside the square root. It turns out. Okay, and so pi has this constraint that its first marginal is mu and its second marginal is nu. And it turns out this is much easier to handle. It turns out to be a problem of what some people call linear programming, and it was well studied in economics. But it turns out that if I take this square root and just look at this quantity, it defines a good old-fashioned metric, a way to define distance. As a metric, just like in the analysis books, where you check the properties, symmetry, triangle inequality, and so forth. And it's a way to really consider kind of geometry on the space of probability measures. And think of it really as a geometric object, the whole space together. And it turns out that that rho, that interpolation measure that I discussed just a few minutes ago, satisfies this property. That if I look at the distance between rho t and rho s, it's just t minus s times the distance of the endpoints. And this is a hallmark to say that this rho here is really a geodesic in this space. It's really kind of an optimal path joining the mu and the nu. It was an interpolation, just a path joining them. But if you look at the right quantity, it's really a geodesic. So I've schematically written that here. And so if you give me two measures, I can find a path. I wrote v schematically, and it's really a best path. I had the assumption that the mu had to be absolutely continuous, but this is actually, this holds in generality, and we could actually even consider our original problem, the one that I said I didn't have an answer to in multi-dimensions. as kind of a problem of, well, I can start out at some measure in some direction, but can I infinitely extend this? Can I take this path and just keep going further and further? And it turns out we don't know how to do it. So on this space so this schematically here in this purple, it's just some infinite dimensional space that I couldn't draw for you. But I can always join between 2 points I can join a path of least length. But if I start out optimally, in the sense if I start out geodesically, can I continue that path? And unfortunately, it's a no. So that's most of the story that I know about these equations. But there's one more application that I want to talk about. And it also ties in with IPAM, as you'll see just shortly. So, okay, Hamilton-Jacobi equations. So these equations go back. I mean, back as far as Monge in the 1800s, with Hamilton-Jacobi trying their best to understand how to solve, how to analyze various problems in mechanics. And one thing that they observed is that in a simple mechanical system, when you have Newton's law, you might have one particle moving subject to a potential or just moving freely. There's an interesting differential equation that arises. And so I'll just give you an example here how that can come about. But here's a minimization problem. And now I'm just thinking of, I just take the kinetic energy of trajectories and I minimize amongst all trajectories that just are fixed at some point x. So you give me a point x and I look at all trajectories from 0 to t that meet x at time t. And so they could be in RD. Okay, and it's known for a given x, a straight line will sort of do the job here. So my point here is just to show you how these differential equations arise rather than talk about some interesting physics. And so this thing here I called either the least action integral. This thing is an action, and so I could talk about the least action. Some people call it a value function. And what's special about it, long after, maybe 100 years after Hamilton-Jacobi, was that these types of objects came about in control theory. And what was known is that there's a way, you see, usually when you're trying to do a minimization, you say, okay, well, let's fix x and fix t and just find the optimal path. But instead, I will really look at this as a function of x and t and study this as its own function. And the reason is because this optimal value here, there's a relationship between them. There's a relationship between this problem, so say, I mean, I could let x be a specific vector, t be a specific time, but it pays off to let these values vary, and then there's a so-called principle. We call it dynamic programming, which basically says that if I know if I know this function really well, then I can just go to a time closer to t, say call it tau, and then do this integral from tau to t, and do this minimization, and I get the same answer. And if I look at this infinitesimally, it turns out that I can derive a differential equation, like so, and it's called the Hamilton-Jacobi equation. Okay, like I said, the physics was pretty easy here. I didn't want to do anything too complicated, but just to illustrate how this equation comes about. Now, this is another example of how I can take this function. It looks pretty wild here. It's an inf of a bunch of things, and say it's a solution to a differential equation. I mean, in fact, Bellman was really confused about this, and it took another 30 years or so before Crandall and Lyons and various other people got involved and said, actually, there's a way to interpret this function as a solution, where I just need the function to be continuous. So that's subtle. Maybe I'll say that again. So usually when you write down a differential equation, you want to take derivatives and just see if everything matches up and you get 0. But here, we actually know that the function probably won't be differentiable, but we still want to talk about a differential equation, or it being a solution to a differential equation. It turns out, in this case, you can. All right? And now, okay, this is work from a long time ago, motivated from work in the 1800s, but it plays in with some current interests. Okay, and really tell you about that. Actually, how am I doing on time, by the way?
10 minutes.
Good. I will need less. Okay, so let me just remind you here. This is really just this is more to fixed notation. So if you give me a function f in RD, and I want to talk about its derivative, really the way I think about that is, well, close to x, f of y is just this linearization. It's just the value at x plus some linear function plus something that goes to 0 when I divide by y minus x. That's differentiability. Okay? So in this xi here, whatever is this xi is the derivative. It just has to be. This is just the definition. Okay. Now, in that space that we were just working with, the space of probability measures, the space in purple, the one that I said I couldn't draw for you because it's a big space. Well, it's a metric space, but it's kind of it kind of almost has a differentiable structure. Not quite. It's not like a manifold where you can really think of derivatives, but nevertheless, in some cases, I can talk about a derivative. And so if I have a function f on this space, so this is the space of probability measures with that metric that I wrote down. You won't need to know it, but just know that there is a metric there. Well, if I can write f at a point close to f at, say, mu, in the following way, plus a term that goes to 0 when I divide by the distance between mu and nu, then this xi is the natural candidate for the derivative of f, okay? And it's a little bit more complicated than I'm writing here, if you happen to be following the details. This pi that I'm writing here is really kind of an optimal measure in the big function defining the w. But let's just ignore that for now, because it's easier to look at. But basically, if you can write f close to f of mu like so, then this xi is a derivative, and it's really its own mapping. Right? It's really its own mapping. C depends on x, and I can measure its size just by taking the so-called L2 norm. Okay, the reason why I bring this up is because, so a lot of times people ask me, like, what are you interested in? What are people doing? A lot of the differential equations we know everything about. Well, some equations that we don't know very much about are equations where a variable is not just t or x. A variable itself comes from the space of probability measures. And this is the type of equation where you're studying large systems. So either large systems of particles that interact, or maybe competing systems, or systems with many agents. And various equations, when you have big systems, if you take an appropriate limit, you get a single equation where one of the variables is a probability measure, one of the variables. So you need to do calculus in some way, perhaps as I've suggested, or maybe in another way to account for this. Okay, and just to illustrate, how could that come up? Well, I can look at an action, a least action integral, very similar to what I did before. There's some function where rho of 0, that's there, and then I'm integrating from 0 to t, and this represents like a kinetic energy. Okay? Where v here is so I'm thinking of taking the minimums over rhos, where rhos are paths in the space of measures, where I have this v, and rho and v together satisfy the continuity equation. That's kind of like saying that the derivative of rho is v in an abstract sense. And then I want rho of t equal to mu. And it turns out, through a lot of efforts of researchers nowadays, I got involved a little bit, but I'd say probably starting with actually some research here, Wilfred Gangbo and some of his co-authors, and there's also Luigi Ambrosio and Jin Feng in Kansas. Now there's a pretty good theory for Hamilton-Jacobi equations in the space of probability measures, where this derivative is, well, it's closely related to the thing that I showed you on the previous slide, measured as how I showed you on the previous slide. And again, this variable, u here, a variable here, is in the space of measures. And so this is a topic of current interest. And I wanted to echo what we heard earlier, I think maybe from the director of IPAM, but who was saying something about we need to advertise all the programs and all the great thing that's happening. Well, I'm helping to organize a summer school this summer at IPAM on various equations like I talked about today, except the topic will be more in game theory, where the particles compete, or the agents, I shouldn't say particles, but the agents compete. And so it'll be a 2-week summer school here on Meanfield Games. The deadline is soon, though. It's a week from today to apply for funding. I hope many of you will consider doing so. Thanks for your attention.